Hello, and welcome back to another IB Math speedrun with me, Vince. In this speedrun, we're going to be going through chapter 10.2, which is all about operations with complex numbers in their polar form. So let's jump right in. So let's start with addition. And the thing is, if you're trying to add two complex numbers in polar form, you almost always have to convert back to the Cartesian form in order to add them. Because what polar form does is it expresses numbers geometrically. And so the thing is, to add these two numbers together, we really have to construct a rectangle with these two as points. Actually, that's a pretty bad rectangle. And so we would get this. But in order to do that, we would have to convert back into Cartesian form. So yeah, we need to skip addition for now. But next, we can do multiplication by a scalar, and that one is quite easy, since we already have the magnitude of the polar number as its modulus. So, say if we have z is equal to rcis theta, then we have that lambda z, where lambda is a real number, is equal to, just lambda r cis theta. Except that this isn't technically true, because the modulus, or the magnitude of the polar number, can only be a positive number. You can't have a negative magnitude. And so the trick we have to use is that it's only equal to lambda r cis theta for when lambda is greater than 0. Of course, it's equal to 0 when lambda equals 0, but for negative values of lambda, we need to rotate the polar number 180 degrees, or pi radians, around the origin, which will convert it from positive to negative. So in this case, we still have absolute value lambda times r, and then we have, instead of cis theta, we have cis of theta plus pi. So this is how we multiply by a scalar when lambda is less than 0. Okay. So that was multiplication by a scalar, by a real number, but how about multiplying two complex numbers together? Well, if we have one complex number, r1 cis, and we have the second complex number, r2 cis, well, what we find is that if we're trying to multiply these numbers together, this is equal to r1 times r2 times cis. But instead of multiplying theta 1 and theta 2, we actually just add them together. So therefore, multiplication by polar numbers, you can prove this, is that if we have two polar numbers, and we want to multiply one by the other, we multiply the magnitude of this existing number by another number, and then we rotate it theta degrees anti-clockwise, where theta is the argument of the second polar number. So with that being said, let's jump into some questions. So I'll do the odd ones. So we have multiply the complex numbers in Euler's or polar form. So first we have z1 is equal to 2. I'll just write these out. So the first case is we have z1 is equal to 2e to the I pi over 3, and we have z2 is equal to 4e to the I pi over 4. And with this, this is even simpler to prove in Euler's form. In order to multiply these two numbers together, we can simply multiply them together. So we have 2e to the I pi over 3 times 4e to the I pi over 4, which is equal to 2 times 4 times e to the I times e to the pi over 3 times e to the pi over 4. So what we have resulting from this is 8 e to the I times e to the pi over 3. And if remember, when we're multiplying exponents with the same base, then we simply add these two. So we need to add pi over 3 to pi over 4. So this is 4 pi over 12, 3 pi over 12. So 8 e to the I to the 7 pi over 12 is the correct answer. Nice. Okay, and then on to the next one. And the next one is we need to multiply 2 2/3 e to the I 11 pi over 7 and 5/6 e to the I 23 pi over 14. Okay. So again, to multiply this, we multiply the modulus, so that would be 10 over 18, so that would be 5 over 9, e to the I, and then we add these two together. So this would be 22 plus 23, which is 45 over 14 pi. Yep, that is correct. Okay. Next question. So, given the numbers, we're given the numbers z1 is equal to CIS 3 pi over 4, and z2 is equal to -1/2 plus square root 3 over 2i. We need to find z1 in Cartesian. Let me write this. We need to find z1 in Cartesian. We need to find z2 in polar. We need to find z1 times z2 in both forms. And find the exact values of sine 17 over 12 pi and tan 17 over 12 pi. Okay, so let's first find z1 in Cartesian form. So z1 in Cartesian form is equal to cosine 3 pi over 4 plus I sine 3 pi over 4, and we can convert this. 3 pi over 4, cosine 3 pi over 4 is equal to negative square root 2 over 2 plus I, and then sine 3 pi over 4 is equal to the square root 2 over 2. So this is z1 in Cartesian form. Next, z2 in polar form. What do we have? -1/2 plus 3 square root 3 over 2i. And it should be fairly obvious that this is equal to CIS square root 3 over 2. This should be equal to CIS 2 pi over 3. Since cosine 2 pi over 3 is equal to -1/2, and sine 2 pi over 3 is equal to square root 3 over 2. So next we need to find z1 times z2 in both forms. And actually, it's much easier to multiply numbers in polar form, so let's do that. So z1 times z2 is simply equal to CIS 3 pi over 4 plus 2 pi over 3. So this is CIS 9, 8, 17 over 12 pi. And it's also equal to, if we simply just multiply z1 and z2 in the Cartesian forms, we have negative square root 2 over 2 plus square root 2 over 2i times -1/2 plus root 3 over 2i. So if we multiply this out, we get square root 2 over 4 minus square root 2 over 4i minus square root 6 over 4i minus square root 6 over 4. So this is equal to square root 2 over 4 times, oh actually no, it's just equal to, what is this, square root 2 minus square root 6 over 4, this is negative 2, so this would be minus square root 2 plus square root 6 over 4i. Actually, sorry, this is minus, this is plus. Wait, what? No, that's not plus. This is minus. Okay, so finally find sine 17 over 12 pi and tan 17 over 12 pi. Well, the thing is, we know this is equal to CIS 17 over 12 pi. So this component over here must be equal to sine 17 over 12 pi, since this is equivalent to cosine 17 over 12 pi plus I sine 17 over 12 pi. So sine 17 over 12 pi must be equal to this part. So sine 17 over 12 pi is equal to negative square root 2 plus square root 6 over 4. And then tangent of 17 over 12 pi is equal to, it's sine over cosine. So this would be equal to negative square root 2 minus square root 6 over square root 2 minus square root 6. So this would be tangent 17 over 12 pi. Can we simplify this? Maybe we can simplify this. So let's try and rationalize the denominator. Negative square root 2 minus square root 6 times square root 2 plus square root 6, all divided by 2 minus 6. So what do we have here? We have negative 2 minus 2 square root 3 minus 2 square root 3 minus 6 all over negative 4. So this is equal to negative 2 minus, oh no, wait, but this is negative, so this is just equal to 2 plus root 3. So yeah, this is tan 17 over 12 pi. Nice. And then on to the final question. We need to calculate the following product. So we need to calculate sine pi over 12 plus I cosine pi over 12 times sine pi over 6 plus I cosine pi over 6 times sine pi over 4 times I cosine pi over 4. And so the thing is, we need to convert all of these into geometric first. And so we know that this number is equal to cosine pi over 2 minus pi over 12. So we can use this to our advantage. And the same, of course, for this is I sine pi over 12. So we can say this is CIS pi over 2 minus pi over 12 times CIS pi over 2 minus pi over 6 times CIS pi over 2 minus pi over 4. So this is simply equal to CIS 3 pi over 2 minus pi over 12 minus pi over 6 minus pi over 4, which is CIS. Convert all of this into over 12, so 18 pi minus pi minus 2 pi minus 3 pi over 12. So this is equal to 12 pi over 12. So it's just equal to pi, which is equal to -1, I'm pretty sure. Yeah, so this is all equal to -1. So that was all for the speedrun. I hope you enjoyed, and I hope to see you in the next one. See you then.